Hey guys, welcome to another video. We finally reached the very end of the IGCSE physics syllabus, and we're going to be going through atomic physics, which has two parts to it. You've got the nuclear atom 5.1 and radioactivity 5.2, and we'll try to cover most of these today. So, for those of you that are taking chemistry, this should be very familiar. You've got the structure of an atom. Now, all atoms have this sort of setup on the right here. You've got the inner nucleus, which will contain what we call the protons and neutrons, and you've got these electrons that are in orbit around the nucleus. And so, what's important here is that protons always have a positive charge, and electrons have a negative charge. And so in terms of the charges, the protons cancel out the electrons, and you've got neutrons that don't have any charge at all. But when you talk about the weight of these subatomic particles, you'll find that the weight of a proton is equal to the weight of a neutron. So arbitrarily we'll go proton equals 1, neutron equals 1, but electrons, they have no mass at all. They're considered to be weightless. So 0, or very technically, is 1 divided by 1,840. That's the exact mass, but we won't really look into that. So when we take a look at the relative charges and the relative masses of these subatomic particles of an atom, then again you have this sort of table that you'll find where electrons have the symbol E minus, have a charge of -1 and a mass of near 0. Protons, on the other hand, have a charge of +1, but they are relatively heavy, and neutrons don't have any charge, but again, they're as heavy as a proton. So the mass of an atom is completely dependent on the amount of protons and neutrons, because those ones are the ones that create the mass. But in terms of the charge of an atom by definition means it has no charge. It's neutral. So what do you think that means in terms of the electron number and a proton number of an atom? Well, given that an atom by definition means it doesn't have any surcharge, what it means is that in an atom, the number of electrons should always equal the number of protons. Because if you think about it, if you had more protons than electrons, you'll have a surcharge of some sort of positive charge. Now, if you had more electrons than protons, you'll have a surcharge of negative. And so, you know, given that that's not the case in an atom, where an atom always has a completely neutral charge, then in an atom, electron number always equals proton number. Now, what is interesting is that atoms can lose electrons, okay? So for example, let me rub out everything here and go back to the slide. Here, how many protons do you have? Well, you've got 2 protons, so that's a +2 charge, right? How many electrons do you have? Well, you've got 2. As I said, this is an atom, so you've got -2. And so you can see that they balance out, and therefore the overall charge is 0. Now, what could possibly happen is that an atom may lose electrons. So you could possibly lose these 2 electrons. These 2 electrons might go away. And so if you were to just get rid of these 2 electrons, then what is the overall charge left over in this particular molecule now? Well, it's a +2 charge, but now that it's charged, we don't call it an atom anymore. It's the atom has officially become what we call an ion. An ion is basically when an atom becomes charged, when electrons become gained or lost. Now, interesting concept here is, for the most part, protons don't move anywhere. They stay in the nucleus. But what does happen is the electrons can be gained by the atom, or it can be lost by the atom, and when it gains or loses electrons, that causes an imbalance between electron number and proton number, and that can result in the atom becoming an ion. But, you know, I digress. It's not really that important for you to know how atoms change into ions here in this physics course anyway, but chemistry is quite important. But the main takeaway here, I would say, is that the concept of proton number of an atom is, as you might guess, is simply the number of protons. The proton number of this particular atom I have on the right is just 2, a proton number of 2. You can also call it atomic number as well. And another important concept is the nucleon number or the mass number. And the mass number is basically just neutrons plus protons, which is the bulk of the mass inside the nucleus. So here in this particular scenario, the nucleon number or the mass number is 4, because 2 neutrons plus 2 protons gives you 4. That is the nucleon or mass number. Okay. So what makes an atom unique? Well, we know that there are around 109 different atoms that we know of exactly, and carbon, oxygen, hydrogen, all these things, or anything that you find on the periodic table, these are all different types of atoms. Now, each atom is unique, okay? And so a substance that you make completely out of just one type of atom is what we call an element. An element is a substance, and if you look at the substance, it's composed of atoms of only one type of atom. So here, if you take a look at this substance, we're going to call it substance, say, A. Imagine that each of these atoms that you find in A is just a carbon atom. Okay, carbon atom. Carbon 12, let's say. So what that means is this is a carbon element, because the entire substance is just purely made of carbon atoms, so therefore the entire thing must be carbon, which is a carbon element. And so what makes one atom unique from another atom is that it has a different number of protons in its nucleus, and if it has a different number of protons, then it must have a different number of electrons from another atom as well. And you can see here hydrogen, for example, has 1 proton in its nucleus, and because proton number must equal electron number, it's got 1 electron outside orbiting that nucleus. Now, how does that differ from carbon? Well, you know, if you look at carbon, you've got 6 protons in the nucleus and 6 electrons to cancel that out. And how's that different from, let's say, oxygen? Well, oxygen has 8 protons and 8 electrons, and therefore you can see every different type of atom fundamentally has a different number of protons, and that's what makes it unique, because when you have a different proton number, what you also have is a different electron number. And when you've got a different electron number, then they will fundamentally behave differently, because, you know, they've got different stabilities associated with the different number of electrons that it has outside of its orbit. And so that's what makes an atom fundamentally different from another atom, the proton number, and as a result the electron number as well. Now, we have these things called isotopes, and remember I said that what makes one atom fundamentally different from another is the proton number, or you could also say the electron number. Okay, so what's interesting though is you could have 2 atoms that have the same proton and electron number but a different mass number. So how does that come about? Well, that's when we look at isotopes, which are variants of the same atom. So as long as 2 atoms have the same proton number, they're considered to be the same atom, but you can have different types. So you can have one atom, for example carbon 12 here, where you've got, you know, 6 protons and therefore 6 electrons, but you have 6 neutrons, making the mass number 12 here. But you can have carbon 13, where you have, remember, the same protons, same electrons, but this time you have 7 neutrons, so that gives you a total mass number of 13 in this case. So they're the same atom, but they're different, and they're different variants. And so carbon 12, 12 stands for 12 as the mass number, and carbon 13 is an isotope of carbon 12, where it's got 13 as its mass. And, you know, you can look at carbon 14, which is a similar situation, where this time you've got 8 neutrons, so the total mass is 14 instead of 12. So you've got these 3 different variants, and when you've got a different neutron number but the same proton and electron number as you see with carbon 12, 13 and 14, well, that's what we call isotopes. So let's just take a look at nuclear fission and fusion very briefly. So you've got 2 different nucleuses that can interact with each other either by fusing or breaking apart into smaller pieces. Nuclear fusion, as you might expect, is the process by which two light nuclei combine together, and that's sort of the definition of fusion, right? And that releases energy as it combines. Now, nuclear fission is sort of the opposite. It's when an unstable, big and large nucleus splits apart into two smaller nuclei, which is sort of what we're exemplifying here in this diagram. One becomes sort of two, or if not more, so you've got some fission and fusion, which is a little bit different from each other. So let's take a look at the concept of a nuclide. So for any given atom, remember, you've got a specific proton number, and that proton number is exemplified by the letter Z, okay? And that's, again, simply just the number of protons that you have in the nucleus. The nucleon number is exemplified by the notation A, which is, remember, the sum of protons and neutrons that you find inside that particular nucleus. The nuclide of an atom just represents these values as a whole in this particular format here. So you've got the nucleon number, right here, remember, which is just the mass number, which is neutron plus proton. And at the bottom here, you've got the proton number, which is simply just the number of protons, and finally you have the element symbol. And as an example of this, you know, oxygen in the nuclide format would be something like this, where you've got 16 as the nucleon number, which is just 8 plus 8. 8 protons, 8 neutrons. You've got the symbol of oxygen, which is O, and you've got 8 as the proton number, which is the atomic number, just the number of protons inside the nucleus. So this is the nuclide of oxygen. So finally, let's just take a look at you know, the discovery of the nucleus. And basically, they carried out an experiment using this sort of gold foil experiment, they call it, where they sort of discovered, or they observed some things from it, and they were able to deduce and interpret what those observations meant. And this is actually quite interesting. So what happened was the experimenters, or Rutherford, basically fired these alpha particles, which have a positive charge. And he fired it at towards a thin gold foil, and you can see that this is what it's doing now. You've got the radioactive source, and through that you're going to fire off these positive particles, and you're going to fire it at this gold foil here. And so the pathway of these positive particles as it passes through the foil after it collides with the foil was observed, and those observations were interpreted. The first observation that they saw was these alpha particles, these positive particles. Some of those, or most of them in fact, most alpha particles travel through the foil without any change in direction. So the bulk of these here, you can see that the direction or the movement hasn't changed from the initial beam that was fired towards the foil. Most of them didn't change directions at all. So what it means is most of these alpha particles are not colliding against anything. It's just going straight through the gold foil. What it means is that most atoms are pretty much completely empty space. The nucleus of the atom is actually relatively very small compared to the atom, and which is why when you fire things at the gold foil, most of these small alpha particles are just missing the nucleus completely, and in other words, they're not colliding against it and changing direction, because of the fact that overall the nucleus is very small and it doesn't take up a lot of space. So that's the first interpretation. The second interpretation, or the second observation I should say, is that there are some alpha particles that were deflected by small angles. So here you can see that you know, the alpha particle has deflected a little bit from its original pathway. And what does that mean? Well, what that suggests is that whatever the alpha particles are colliding against within this gold foil must be positively charged, because of the fact that like charges repel each other. That's how you deduce it, right? Because otherwise they'd be attracted, but you can see that there's a deflection that goes on, and there's a push away from the source. So as the positive particles come through, the observation is that it got deflected, and we were able to interpret that, okay, well, whatever this alpha particles are colliding against, which we know is the nucleus of the atoms of the gold foil, must be positively charged, because same charges repel each other. And lucky last, we found that some alpha particles actually become reflected backwards like this one here, instead of going through the gold foil. And what that exemplifies is that the nucleus carries most of the atom's mass, because as it hits the nucleus, some of it will collide against it and jump right back towards us. And so if it doesn't hit the nucleus, then it sort of just goes straight through. Okay, so when it hits against the nucleus and it hits it at a right angle, it comes back towards us, and so therefore we know that electrons, they don't play a role. Most of the things in the atom don't really have any sort of mass to it except for the nucleus itself. They're right at the center, very dense, pretty heavy, and when something collides against that, then again you can get this where it sort of gets reflected back towards us. So we're just going to have a look at radioactivity, which will be the very, very last part of this syllabus content. And so we're going to think about something called radioactive decay, which is basically a spontaneous transformation that occurs in an unstable atomic nucleus, which as a result releases radiation in the form of these particles called alpha particles, beta particles, or gamma rays. So if an atom has a nucleus that is unstable, then it can try to stabilize itself by releasing this radiation, and that's radioactive decay. And so depending on what sort of particle is being emitted in this radioactive decay, then you can either have alpha decay, which is where you release the alpha particle. You've got the beta decay and the gamma decay, and each of these are different. So in alpha decay, which is this one here, the alpha particles are emitted from the original nucleus, and each alpha particle is equal to a helium nucleus. A helium nucleus contains 2 protons and 2 neutrons, which, remember, has a Z number of 2 and A number of 4, because 4 is the mass number, which is 2 plus 2, and Z is the atomic number, which is just 2 numbers of protons. And so basically this here represents alpha decay. You have an original mass of 222, an original proton number of 88. In alpha decay, you have the emission of an alpha particle, which is equivalent to a helium nucleus. So it's this one here, which is also alpha. And so as a result of that, when you take away 4 mass from the original 222, you're left with 218, and as a result of the fact that you lost 2 protons, again, 88 minus 2 becomes 86, so that is the remaining atom from the decay, and you get the release of the alpha particle, which is equivalent to a helium nucleus. In beta decay, I'll clean this up a little bit. In beta decay, you have a neutron that is converted into a proton and electron. So you've got to think about this a bit more carefully. The electron is fired out of the nucleus, whereas the proton remains. So if you think about it, as a result of this decay, the neutron number will go down by 1 and the proton number will go up by 1, because the neutron is being converted into a proton. So the proton number goes up and the the neutron number will go down. So here carbon-14 is going to go through this beta decay, and so what you'll find is that you have exactly the same mass number, because the mass will stay the same given that a neutron has changed into a proton, but what has changed is the proton number goes from a 6 to a 7. Okay, and so you have 7 protons and 14 total mass in this new atom, and you get the release of an extra electron, because remember, the neutron has converted into a proton and an electron, and that results in an increase in proton number and one release of an electron number, whereas the mass number stays the same. The gamma decay is the most easiest form of decay, whereas the number of protons and neutrons remain unchanged. The gamma ray takes away some of the excess energy after the nucleus has been emitted, so you find that you don't really get any changes at all happening. You can see that the mass number, proton numbers, is stayed exactly the same, except for the fact that a gamma ray has been released as a result of that decay. So given that we've looked at these different particles, they've got different characteristics, and we can take a look at those characteristics when, in terms of its charge, mass, ionizing effect, penetration, and its behavior in electrical fields and magnetic fields. As mentioned above, we've got the radioactive decay that results in the emission of these particles, alpha, beta, and gamma. So when it comes to the ionizing effect, what it means is that these particles have the ability to remove electrons from other atoms that they collide with. So if you've got a normal atom, let's just say oxygen, that's just chilling along, it's got its electrons hanging around on the outside. When an alpha particle comes along and collides against this oxygen and bounces off it, alpha has a fairly strong ionizing effect, and what it can do is it can remove the electrons from the oxygen. Now imagine if your cells were getting these electrons removed as a result of this ionizing effect. When you have electrons that are being lost like this, then that destabilizes the atom and can cause all sorts of problems. So that's why being exposed to radiation is a very bad is bad for your health as a result of that, and it can lead to cancer and things like that as a result of this instability, chemical instability. But that's what we mean by ionizing effect. And alpha particles have a very strong ionizing effect, beta particles have a fairly weak ionizing effect, and gamma rays have a very weak ionizing effect. So there's a difference there. So once an atom loses an electron, as I said, there's a charge imbalance, so that's what's going there. And so when we take a look at penetration, it's sort of the opposite compared to the ionizing effect. So the alpha particles have the weakest penetration. It becomes absorbed very quickly. Greater penetration as seen in beta particles, and very strong penetration that you can see in the gamma rays. Okay. So if you take a look at the effect of electric fields on these particles, you'll find that gamma particles, first of all, don't get affected at all. If you've got the positive and the negative charge, gamma particles will just go straight through without becoming attracted to either end because they don't have any charge. Now, beta particles are negatively charged, as you might expect. They become attracted to the positive plate, and alpha particles are positively charged, and therefore oppositely they're attracted to the negative plate, and that's why you get the divergence of these three behaviors. So if you take a look at the effect of magnetic fields on these different particles, first of all, you know that anything that has a charge or any current that goes through a magnetic field will be deflected as a result of the electromagnetic effect between the current and magnetic fields. We know that the gamma rays don't have any charge, so they shouldn't be affected at all within a magnetic field, but you know that the alpha particles are positively charged and the beta particles are negatively charged, and so when you have a movement of alpha particles or beta particles through a magnetic field, you can consider that to be a current, and therefore you'll get the same sort of electromagnetic effects that we talked about in the topic. One of those things that we talked about was the Fleming's left-hand rule. The index finger represents the direction of the magnetic field, and in this case, because the magnetic field is pointing out of the page and towards you, your index finger will be pointing towards yourself. The second finger, this middle finger, represents the direction of a current, and remember, conventional current is a stream of positive charge. So if you do that with the alpha particle, with the index finger being pointed towards you and the current pointing towards the right hand side, then you'll find that your thumb is going to go downwards, and that's the direction in which the alpha rays get deflected, and that's why you see the alpha particles sort of going down as it passes. Now, the beta particles have a negative charge, which is why the way that they behave will be different. And if you were to utilize the Fleming's left-hand rule for this, you'll find that, first of all, that first finger will be pointing towards you, but in this case, the beta particles are moving in this right direction here, but because beta particles are negative and conventional current is positive, you need to reverse the direction so that the middle finger is going to the left. And when you do that, you'll find your thumb pointing upwards, and therefore, beta particles are going to be deflected upwards in this magnetic field. The most important thing, remember, is conventional current being used with that middle finger, or that second finger, and so that's why you have to reverse the direction in which these beta particles are moving. And the last thing we want to talk about is half-life. We've had a look at the idea of radioactive decay. So a sample of a radioactive decay or material will decay, and the activity of that decay will inevitably decrease over time. Now, the activity is the number of radioactive particles that are emitted per second. As the number of unstable nuclei decreases, well, the number of emitted particles will become decreased too, and generally the activity will become lower and lower and lower. But sometimes it's truly difficult to assess when the sample of a radioactive material completely stops to zero, because it really never does. The activity will still sort of continue, it's just at a very slow rate. So sometimes, instead of sort of tracking when exactly it hits the 0 point, which is difficult, what we can do is measure how long it takes for a sample of a radioactive material isotope for it to halve its original activity. So the time taken for the activity of a sample to fall to half of the original value, and that is what half-life is. You start off, let's just say, a percentage of 100, and then you measure how long it takes to get to half of that, which is 50. Then you measure how long it takes to get half of that, which is 25. And each of these blocks, those are half-lives, as you can see on the graph. And last point of safety precautions, as I said, ionizing radiation can kill or even damage human cells by causing the cells and the atoms within those cells to become unstable. This can lead to DNA mutation, and that can lead to cancer. So people that are working in this sort of environment exposed to radiation, it's important that you try to keep safe from that. So radiation workers wear film badges which monitors the dose of radiation that they're being exposed to, along with other, safety precautions in regards to helmets and, clothing that can block off the radiation. But pretty much all these safety measurements are there to allow them to make sure that they're not being overly exposed to the levels of radiation that can possibly cause some severe consequences, as I said, like cancer and such. So the detection of radioactive activity, you can use a GM tube or a photographic film for that, and this isn't really a big part of the syllabus, but we'll briefly cover it. A GM tube detects ions produced when an alpha or beta or gamma radiation enters the tube. You can have a further look into this on YouTube to see exactly how it works, but the very basic idea is that it's attached to a counter that just basically registered a count each time a radioactive particle is detected. So fairly simple. A photographic film is basically a film that becomes blackened by the presence of ionizing radiation. So this just sort of measures whether a ionizing radiation is present or not necessarily an exact quantitative measurement of exactly how much, but the higher the number of radioactive particles, the blacker it does become. So you can still judge the levels. The more blacker it is, the more radioactive presence that you've got, but ultimately that's one other way that you could look at it as well. So I hope this video was helpful, guys. Take a look at freeexamacademy.com. That's where I put my notes for physics, chemistry, and biology. You can find that there, and you've got my Patreon channel where I cover exam prep, specific paper 4, paper 6, paper 1 questions, and things of that nature. I will be putting a lot of physics material on there very shortly, but I do already have a lot of chemistry and biology ones there, so for those of you guys that are taking that, I'd encourage you to have a look at that, and I will see you in the next video.